Here's an example of the maximum power transfer theorem. We're given the circuit to the left, and this is a circuit that's going to deliver power. And it's going to deliver power to our load. And I'm going to call it Z sub L. I'm going to keep it at the schematic diagram for Z sub L as a box, because perhaps it's a resistor, perhaps it's an inductor, a capacitor, or some combination of them. Our goal is to figure out what Z sub L should be so that it receives the maximum amount of power from the circuit to the left, and then find out what that maximum power is. So the first step is from our previous slide here. In order for Z sub L to dissipate the maximum possible power, we need to find the Thevenin equivalent to the left. Once we find the Thevenin equivalent, Z sub L is going to be equal to the complex conjugate of the Thevenin equivalence source. And then we can figure out what the maximum average power is delivered to the load by using this equation. So let's figure this out. In order to find, this is our first step then, is to find the Thevenin equivalent to the left of the two green circles. So to do that, we're going to begin by finding VOC, and then we will find Z equivalent, Z source, and then from that, we'll be able to find the Thevenin equivalent. So let's begin by finding what VOC is. VOC is what the voltage is across here. So already we can see we can simplify a few things. These two impedances in the left are in series. We have our 6 amp source moving up. We have our J10 and our 5 over here. And we can't combine our J10 and our 5, even though they are in series, because we want to find what the voltage is across that 5. And that voltage is VOC. It'll be a phasor. So a number of ways we can do this. We could do a nodal. If we did a nodal down here, we'd have 1, 2 unknowns. We'd have to call this V sub 1, and we'd call this VOC, and then we'd call this VOC, and then we could solve. We'd have a 2 by 2. That's not ideal. Let's see if there's something else we can do that's simpler. If we did mesh, we'd say this is going to be a super mesh around here. And that would find this outermost current, but then we'd have to do an extra step to find what VOC is. We'd have to be 5 times the part of the super mesh that's on this side. So it's going to be 1 super mesh, plus we'll have to have an additional step afterwards to convert from the current to VOC. Not bad, but I think my first instinct would be to do a source transform and see if that makes things a lot easier. So by doing a source transform, we end up having, we'll multiply these two things together and we'll get 6 times 8 minus J4. Maybe I should actually literally just multiply those things. So 8 times 6 is 48 minus J24. And that is going to be our new voltage source. Now this is going to be in series. That will be in series. And this looks a whole lot better. Now it's just a voltage divider. And now we can directly find VOC by saying it's equal to the source times the voltage across which we want to find, which is our 5, plus all of them sum together. So sum together is 5 plus 8, which is 13, let's see, minus J4 plus J10 would be plus J6. And we can put that into our calculator and find it's equal to 18.7 at an angle of minus 51.3 degrees. So that's our first step. Our next step is to find not what the VOC is, but to find what the Z equivalent is. Now we could have found what I short circuit is, which would require a similar amount of work, and then divided VOC into IC to find ZEQ. But it's usually faster to find ZEQ directly, especially if we don't have especially if we don't have dependent sources. So let's see how to do this. We want to find ZEQ, again, from our diagram up here. We zero all of our sources, and a 0 amp current source is just a open. And our goal is to find out what the equivalent impedance is looking into this. So I think it's pretty clear that these two are in series. So that gives us 8 plus J6. And the 5 is in parallel with it. So it's going to be whatever 8 plus J6 is in parallel with 5, which is equal to product over sums. 5 plus 8 is 13 plus J6. So that is 3 in our calculators, 3.42 plus J 0.732. Now we found the answer to step 1. This whole circuit to the left looks just like an 18.7 at an angle of minus 51.3 voltage source in series with a 3.42 plus J 0.732 impedance. So drawing it just like we did above, now we can simplify this dramatically. And now we can solve the problem. Z load is equal to the complex conjugate of Z source. So it's going to be equal to 3.42 minus J 0.732 ohms. Now, I didn't tell you what the frequency was. If I did, you could simplify this into a resistor of 3.42 and a series capacitor. You know it's a capacitor because it's a negative imaginary number. And you could have figured out what that capacitance is because you know that the impedance of a capacitor is equal to 1 over J omega C. That's the impedance of a capacitor. That's equal to minus J over omega C. But here we said that has to equal to minus J times 0.732. So you can divide both sides by negative J and find out that 1 over omega C is equal to 0.732. And you could solve that. If you knew what omega was, you could solve that for the equivalent capacitance. But the best that we can do is, since we don't know what omega is to say this is the ideal load impedance that will cause it to dissipate the greatest amount of power. And then the second question is, what is that power? And that's the formula we derived on the previous screen. We said it's equal to the magnitude of V sub S squared all over 8 times the real part of Z sub S. So that's going to be our V sub S. Let's see, the phi sub s we said here has a magnitude of 18.7. The real part of z sub s, the real part of this is 3.42. And when you plug that in your calculators, you'll get 12.8 watts. So these are the answers to the question.